Okay, good morning. In the previous lecture, we have discussed some of the aspects related to entropy change. Okay, as well as we also tried to quantify the stagnation properties, and then we also saw Hignoy relation for particularly for the one-dimensional flows involving soft waves. Okay, now one important point. In the last lecture, just I made a mistake. So when we estimated the value of P2 by P1, particularly for M1 approaches to infinity. So in the denominator, there was one division by M1 that I have missed actually. So this ratio of P2 by P1 will become infinity. Okay. So please make this correction. So on the slide 1, particularly on page 1, when I have derived the value of P2 by P1, when m1 approaches to infinity, so that ratio of p2 by p1 will become infinity. Okay, then at the end of the lecture I told you that if I have nothing but Hignoy relation u2 minus u1 equal to p1 plus p2 by 2 into v1 minus v2. Okay, so this relation is applicable for a general case. Now if I do substitute over here that u is equal to cv times t and pv is equal to rt, so this type of assumption will be applicable nothing but for a calorically perfect gas. Okay, so this is applicable for calorically perfect gas. Under these conditions, if I do substitution in the Hignoy relation, I will find that Cv times T2 minus Cv times T1 equal to P1 plus P2 by 2 times V1 minus V2. Okay. Then what I can do over here, Cv I can take out common. Okay, because Cv will not be function of temperature for calorically perfect gas, and also we know that from our earlier knowledge that Cp is nothing but equal to R divided by gamma minus 1. So let me take out Cv and replace it with R by gamma minus 1. Then it will become T2 minus T1 is equal to P1 plus P2 by 2 times V1 minus V2. Okay. Now what I can do, this R I can multiply inside. So if I do so, 1 by gamma minus 1 RT2 minus RT1 will become P1 plus P2 by 2 into V1 minus V2. Okay. Now from the relation PV is equal to RT, I can write RT2 as P2 into V2. Okay. So from here I will get 1 by gamma minus 1 P2 V2 minus P1 V1 is equal to P1 plus P2 by 2 times V1 minus V2. Okay, so let's do one thing now. All the terms involving P2 I will keep on left hand side and terms involving P1 I will keep on right hand side. So if I do so, I will get P2 times V2 by gamma minus 1, and from the right hand side I will get minus V1 by 2, and this I will get plus V2 by 2. That will be equal to P1 times because this P1 is shifting to the right hand side, so it will be having positive sign. So I will get V1 by gamma minus 1, okay, plus V1 by 2 minus V2 by 2. Okay. Now what I can do, I can take this 2 into gamma minus 1 over here, and then it will become 2v2 minus v1 will be multiplied with gamma minus 1. So it will become minus v1 gamma plus v1. Then this v2 will also get multiplied. So v2 gamma minus v2. Okay. And in the right hand side I will get similarly 2 times gamma minus 1, and here I will get 2v1 plus v1 gamma minus v1 minus V2 gamma plus V2. Okay. Now this 2 by gamma minus 1 will cancel out in the denominator on both the sides. So I will get P2 times it has become minus V1 gamma plus V2 gamma. Okay, and this plus V1 and this 2V2 minus V2 will become plus V2. Okay, and this will be equal to P1 times V1 gamma minus V2 gamma plus V1 plus V2. Is this one clear? So from here, if I divide on both sides by V1, what I will get? P2 times minus gamma, sorry, if I divide both sides by V2, okay, so if I divide both sides by V2, I will be getting minus V1 by V2 gamma plus V1 by V2. Okay, is this one clear? Plus 1, and this will be equal to P1 times V1 by V2 times gamma minus gamma plus V1 by V2 plus 1. Okay, so from here now let's calculate P2 by P1. So if I calculate P2 by P1, it will become, in the right hand side, what I will do, V1 by V2 I will take common. So if I take V1 by V2 common, I will get gamma plus 1. Okay, is this one clear? So I am getting V1 by V2 times gamma plus 1, and this thing will become minus of gamma plus 1. Okay, minus of gamma plus 1 divided by, now in the left hand side, if I take V1 by V2 common, then what I will get? I will get, let me take minus V1 by V2 common. So if I take minus V1 by V2 common, inside I will get gamma minus 1. This will become gamma and this will become minus 1. Okay, so gamma minus 1, and here I have gamma plus 1. Fine. Now what I can do, I can divide both numerator and denominator in the right hand side by gamma minus 1. Okay, so what I will do now, numerator and denominator both I will divide with gamma minus 1. So both quantities, if I am dividing by the same number, same quantity, then it will remain the same. Okay, so P2 by P1 will become V1 by V2 times gamma plus 1 by gamma minus 1 minus of 1 divided by gamma plus 1 by gamma minus 1 minus of V1 by V2. Okay, so this is what I have asked you to calculate in the last class. Okay, so this is nothing but, this is Hignoy relation. This is Hignoy relation for calorically perfect gas. Okay, is this one clear? Now what we will do, we will try to see some another situation. Okay, so Hignoy relation and whatever the earlier formulation we have done, these were applicable when in one dimensional flow situation we were having the presence of shock wave. Okay, so now whatever the changes made by shock wave on the fluid element, these changes can be made by some other phenomenon. such as heat transfer and friction, etc. Okay, so we will now try to see the one dimensional flow situation, 1D flow situation with heat transfer. Okay, so what I said, in case of our earlier control volume, what we were having basically a control volume like this, and inside this control volume I was considering that I am having nothing but the presence of a shock wave, and this shock wave was actually resulting in change of properties on its upstream and downstream. Okay, so now this change, other than the shock wave, so particularly if you see, in case of shock wave we were not having involvement of any heat transfer, and also we assumed that our flow situation is inviscid. Okay, however, whatever the changes we have observed in case of shock wave, these changes we can observe in some other type of situations as well. Okay, so two important situations which we will be encountering in many of our high speed, many of components involving high speed are flows involving friction and flows involving heat transfer. Okay, so one typical example is if you have natural gas pipelines. Okay, so say your gas exploration is being done in some location 1, and then you have to transport that natural gas to some other location, say which is thousands of kilometers away from your exploration point. Okay, so you will be having a long pipeline which will be having length of about thousands of kilometers. So in that long pipeline there will be nothing but the significant amount of friction involved, because whenever there is a flow of fluid in a conduit, there will be nothing but wall shear stress. Okay, so that wall shear stress will cause certain changes in the flow parameters. So it is interesting to know that how friction actually changes the properties of the fluid behavior, because whatever the natural gas you are transporting, that will be having its certain self ignition temperature. Okay, so if say your friction is high enough that it is causing the total temperature or stagnation temperature of the gas to go beyond its say beyond its auto ignition temperature, then there may be chances of fire, etc. Okay, so we have to actually analyze these situations. So that is one important aspect, that friction can also cause significant changes in the properties of a flowing fluid when actually the length of the conduit is very large. Second important point is heat transfer. Okay, so if you analyze your rocket engine or say ramjet engine, turbojet engines, so mainly the engines which we use in our spacecrafts or aircrafts, etc. So in these engines we will be finding that we are having initial, I have earlier also told you, we are having initial first compression section. Okay, say up to this point we have initial compression of the fluid. So after this compression over here we are having nothing but combustion chambers. So this is my combustion chamber. So what happens basically inside a combustion chamber? Inside a combustion chamber we see that these hot gases which are coming from here, these react with the fuel, and then oxidation of the fuel takes place, which releases large amount of heat. Okay, so we are having here release of large amount of heat, and upon the release of large amount of heat, here we experience that our pressures and temperatures are actually extremely high. Okay, so at the end of the combustion chamber we will be finding that pressure and temperature is extremely high. Okay, so we have to understand this situation. Particularly you might be wondering that when we do analyze our Brayton cycle in case of basic thermodynamics, there we are easily able to do the analysis. So the difference is that when we do analyze the Brayton cycle in our basic thermodynamics course, we don't consider the compressibility effect of the air. Okay, once you include the compressibility effect, our analysis become complicated. Okay, so that is what we will try to see over here. So this is one significant and one very important application where we can see that the addition of heat will be actually resulting in significant changes in its properties. Okay, then another interesting example can be, we may have one a long wind tunnel, and in that wind tunnel, say if we are illuminating some cross section of the wind tunnel with say high intensity laser, high power laser, so that laser will also supply significant amount of heat at that particular cross section, and then there can be significant changes in the properties of the fluid medium whatever we are having in consideration. Okay, so now we will take a situation, where we have a control volume. Say this is my control volume. So at the inlet of the control volume, my state condition is 1, and at the outlet of the control volume condition is 2, and in this control volume, say I am adding Q amount of heat, that is on per unit mass basis. Is this one clear? So you should be able to differentiate. In case of shock wave, if you see here we were not adding any heat. Okay, so whatever the changes were happening, these were actually because of the presence of the shock wave. Okay, and here what we are trying to do, we are not saying that we have already the presence of a shock wave, but all these changes we are studying because of the addition of the heat. So this typical situation holds very well for a combustion chamber of a aircraft engine. Okay, now if I take this particular situation, then what will happen? Here I can write down my continuity equation. So continuity equation, so before that let me define the parameter over here. Say pressure is P1, density is ρ1, velocity is V1, and Mach number over here is say M1 here, and temperature is say T1. So here I will be having pressure P2, density ρ2, and V2 as velocity, M2 as Mach number, and T2 as temperature. So once again, the from the perspective of the fluid flow analysis, this situation is identical to that of shock wave. We know all the conditions at the upstream of the control volume, and we have to predict all these values at the downstream of the control volume. Okay, so what we will do now, we have to apply over here the basic governing principle. So we know that our very first principle is nothing but ρ1 V1 equal to, so this is the continuity one, and then I have P1 plus ρ1 V1 square equal to P2 plus ρ2 V2 square. This is our momentum equation, and third equation will be energy equation. H1 plus V1 square by 2 will be equal to H2 plus. Now can you tell me, is this equation correct? Whatever the control volume now we are considering, whenever we were considering the shock wave, then situation was adiabatic. We were not having any heat transfer. Okay, so that's why this energy equation was correct. But now when we have this Q amount of heat transfer involved over here, so we have to consider the addition of Q amount of heat in our energy equation. Is this one clear? So now another important fact is that we know our Mach number is equal to V square by A square. So from here I can simply say that my V square I can write in terms of A square into Mach number. Okay, and if I take air to be my fluid, which is a calorically perfect gas, so then for calorically perfect gas, A square I can write as nothing but gamma R T times of Mach number. Okay, and RT, in place of RT I can write P by rho as well. So I can write gamma P by rho into M. So it means I can write my V square as nothing but gamma P by rho into Mach number. Is this one clear? Okay, now let's try to write down our V1 square and V2 square like this. So if I have to write V1 square, I can write V1 square as nothing but equal to gamma P1 by rho 1 into M1 square, and similarly V2 square I can write as gamma P2 by rho 2 into M2 square. Okay. Now let me substitute this V1 square and V2 square in nothing but my momentum equation. Sorry? Okay, V1. Okay. It should be M square actually, yeah. Because V by A is Mach number. So this should be, here I have done mistake previously. When I have defined Mach number over here, Mach number is nothing but velocity of fluid upon velocity of sound. Okay, so I was writing over here V square by A square. So if I write V square by A square, then I have to write over here Mach number square. So if this is Mach number square, then V square will become Mach number square, and here also it will become Mach number square. Is this one clear? So initially I have made a mistake. Here it should be M square in place of Mach number. So this is my V1 square will be equal to gamma P1 by rho 1 into M1 square. Fine. Now this value, say if I number these equations as 1, 2 and 3, then this equation number 2, in the equation number 2 I can replace V1 square and V2 square with these numbers. Okay, with these values. So if I replace, then what I will get? P1 plus half rho 1 will get cancelled. So gamma P1 M1 square. Okay. Similarly, in the right hand side, I will get P2 plus half gamma P2 M2 square. And now if I take P1 common, then 1 plus half gamma M1 square will be equal to P2 times 1 plus half gamma M2 square, and I will get from here the ratio of P2 by P1 will become equal to 1 plus gamma by 2 M1 square divided by 1 plus gamma by 2 M2 square. Is this point clear? So it means we have determined the ratio of P2 by P1. Now we have to similarly calculate the ratio of other quantities as well. So we know that P is equal to rho RT. From here I can say that P2 by P1 will be equal to nothing but rho 2 by rho 1 into T2 by T1. Now from my continuity equation I can write rho 2 by rho 1 as equal to, what I can write from continuity equation? V1 by V2. Rho 2 by rho 1 will be equal to V1 by V2. Okay. So it means that I can write this as V1 by V2 times T2 by T1. Now I also know that V1 by V2 I can write in terms of A1 into M1 divided by A2 into M2. Okay, because velocity is equal to speed of sound into Mach number. So let me do this. let me do this. So if I do so, I will get P2 by P1 will be equal to A1 M1 by A2 M2 into T2 by T1. Now for a calorically perfect gas, A1 is nothing but square root of gamma R T1 into M1 divided by square root of gamma R T2 and M2, okay, times T2 by T1. So gamma R will cancel, and from here I will get square root of T2 by T1, because this is power 1, this is power 1 by 2. So this will make it square root of T2 by T1 into M1 by M2. So from this particular formulation, I can say that if I take square of both sides, I can tell that T2 by T1 will be equal to P2 by P1 whole square times M2 by M1 whole square. Is this point clear? So here T2 by T1 I can find as P2 by P1 whole square into M2 by M1 whole square. So P2 by P1 I already know. So if I do this substitution, I will get 1 plus gamma by 2 M1 square divided by 1 plus gamma by 2 M2 square whole square, okay, into M2 by M1 whole square. So this is my another important result, because I have estimated the value of T2 by T1 over here, okay. Up to this point, is it clear? Then we have to estimate the third parameter, and our third parameter is nothing but density ratio, rho 2 by rho 1. So once again I will go back to my earlier formulation, P equal to rho RT, and from here I can tell that rho 2 by rho 1 will be equal to P2 by P1 into T1 by T2, okay. So now I know the value of P2 by P1. P2 by P1 is 1 plus gamma by 2 M1 square divided by 1 plus gamma by 2 M2 square, okay. And T2 by T1 is this. So I have to write T1 by T2. So it means I have to take reciprocal of this entire quantity. So reciprocal of this will become M1 by M2 whole square, okay, times 1 plus gamma by 2 M2 square 1 plus gamma by 2 M1 square whole square, okay. And from here I will get rho 2 by rho 1 equal to, this is power 2, this is power 2 over here, so 1 will cancel from first term. So I will get M1 by M2 whole square times 1 plus gamma by 2 M2 square 1 plus gamma by 2 M1 square. So this is another important result where we have calculated ratio of rho 2 by rho 1, okay. So till now we have utilized only my continuity and the momentum equations along with the relations for a calorically perfect gas, okay. So if I take the energy equation, from energy equation I will get that let me write H1 as CPT. So Cp times T1 plus V1 square by 2 plus Q will be equal to Cp times T2 plus V2 square by 2. Okay. Now we know that this entire quantity is nothing but I can write Cp times T01, stagnation temperature, and this I can write Cp times T02. So from here I will get Q is nothing but equal to Cp times T02 minus T01. So it is interesting to note that when we will be adding the heat, we will be having increase in stagnation temperature of the fluid. This is something why I am saying it is interesting to note, because in case of shock wave where the flow situation was adiabatic, we were not adding any amount of heat. Okay, and in that case we found that our stagnation temperature was remaining constant. Okay, so from the last two lectures, if you recall, particularly for a shock wave, because flow situation was adiabatic, and when we derived the formulation of stagnation temperature, we have come up with the conclusion that stagnation temperature is actually remaining over there constant. Okay, stagnation temperature of the flow was not changing, but over here we are able to see from the conservation of energy equation that when we are adding the heat, the stagnation temperature of the fluid is actually increasing. Okay, so this is one significant change from the previous formulation of normal shock wave. Okay, now till now we have represented the quantities, all the static quantities like static pressure and static temperature ratios and ratio of densities. Okay, however we have to determine the ratio of stagnation quantities also. Why? Because till now we don't have the enough number of equations to give the value of all the variables. For example, can you tell me how many equations I have now? P2 by P1 1, T2 by T1 2, rho 2 by rho 1 3, and 1 is this Q equal to Cp T0 2 minus T0 1. So I have nothing but the 4 equations. Can you tell me the unknowns involved? So all the quantities having subscript 2, these are nothing but our unknowns. So tell me the number of unknowns. P2, rho 2, T2, M2, V2 and M2 both are the same thing. T02. Okay, so we have not, till now we don't have enough number of equations to solve all these quantities. Okay, so what we have to do, we have to now go for more quantities. So more quantities from where we can get, we have two more parameters left, that is nothing but our stagnation pressure or total temperature. Okay, so let's try to determine the equations for these two quantities. Okay, so here I have 5, deficiency of one equation, but if I consider my stagnation pressure also, then I have number of variables as 6. So it means I have deficiency of 2 more equations. So it means now I need to determine the values for stagnation quantities as well. Okay, so let me do so. We know from our earlier knowledge that stagnation pressure by given pressure ratio is nothing but equal to 1 plus gamma minus 1 by 2 Mach number square times gamma by gamma minus 1. So if you recall, I have taken one lecture where I have given you the different alternate forms of energy equation. So in that particular lecture actually this correlation I have obtained. Okay, so this relation I should not call it as correlation, this is derived. So this relation I have actually obtained. Similarly, T0 by T also I have found as 1 plus gamma minus 1 by 2 m square. Okay, now let's utilize these two relations to determine the ratio of P02 by P01 and T naught 2 by T naught 1. Okay. So what I can do over here, I can define that P naught 2 by P2 is equal to 1 plus gamma minus 1 by 2. This will be Mach number 2 square and this whole power gamma by gamma minus 1. Similarly, I can define P naught 1 by P1 equal to 1 plus gamma minus 1 by 2 Mach number 1 square power gamma by gamma minus 1. Okay. Now my aim is to find out P naught 2 by P naught 1. How I can find out P naught 2 by P naught 1? If I take this quantity P naught 2 by P2 and P naught 2 by P1 and multiply it with P1 by P2 or P2 by P2? P2 by P1. What I will get? I will get nothing but P naught 2 by. Okay, so let me do so. So first is I have 1 plus gamma minus 1 by 2 m2 square whole power gamma by gamma minus 1 divided by, sorry, this should be P naught 1. 1 plus gamma minus 1 by 2 m1 square whole power gamma by multiplied by P2 by P1. Just now I have calculated. How much is P2 by P1? 1 plus gamma by 2 M2 or M1? M1 divided by okay. So it means, sorry, yeah. So this is one more equation I have got, which is giving me the ratio of stagnation pressures. Similarly, I have to calculate the ratio of stagnation temperatures. Okay, so if I go for stagnation temperatures, I will get T naught 2 by T2 will be equal to 1 plus gamma minus 1 by 2 m2 square. Okay, and similarly T naught 1 by T1 equal to 1 plus gamma minus 1 by 2 m1 square. Okay, now I have to calculate T naught 2 by T naught 1, which I can calculate like this: T naught 2 by T2 divided by multiplied with T2 by T1. So this will become 1 plus gamma minus 1 by 2 m2 square divided by 1 plus gamma minus 1 by 2 m1 square multiplied with T2 by T1. If you see T2 by T1, it is m2 by m1 square and 1 plus gamma by 2 m1 square one plus gamma by 2 m2 square and whole square of the entire quantity. So from here I have calculated nothing but the value of stagnation temperature. So now I have 6 equations and 6 unknowns. So it means that now I can find out the solution of all the quantities. So what should be the solution procedure? So if I have to follow the solution algorithm, so I can go it like this. In step 1, use relation Q equal to Cp times T naught 2 minus T naught 1, because Q is known, T naught 1 is known. So from here I can find out the value of 2. Once T naught 2 is known, I can now find out the value of, I can substitute this in the ratio of T naught 2 by T naught 1 and I can calculate what is unknown in this entire equation, M2. I can calculate the value of M2. However, one interesting point is that in this equation, this is so complicated that you will not be able to explicitly take out the value of M2. So in this equation, you have to do nothing but trial and error. So you have to suit a value of M2 and then check if it satisfies this equation, and depending upon the trial and error, you have to calculate the value for M2. Is this one clear? So here, because of the complication of this equation, you will not be able to explicitly segregate value of M2 over here. So here you have to go for trial and error method to find out the value of M2. Okay. Once you obtained the value of M2 by trial and error, then third point is easy. M2 is known, M1 is already known. So now you can go to any, say if you go to rho 2 by rho 1, you can calculate. If you go to T2 by P2 by P1. So now if these are calculated, then all quantities like T2 by T1, P2 by P1 and rho 2 by rho 1 can be calculated. Okay. Is this one clear? So you see now, when we have the case of incompressible fluid, we consider that density is not changing. Okay. And with that simple assumption, our situation becomes so simple that we are not concerned about other quantities like with density variation, and we can easily calculate the value of temperature and pressure at the exit. Okay. However, if I introduce just one variable, density change, then my flow analysis becomes so complicated. Okay, so you can see this is nothing but a simple situation where in a pipe you are adding heat to a fluid, but you are considering the effect of compressibility. So by just considering the compressibility for one dimensional situation itself, we have got so many variables and so many equations involved to find out the complete solution. One interesting fact is that if you see this particular formulation from the starting itself, I have considered the assumption of a calorically perfect gas. Okay, so it is important to mention that this analytical solution, closed form of analytical solution, is available only if we consider the assumption of calorically perfect gas. If you consider this for a real gas behavior, then we will not be able to find the analytical solution for this very simple situation, and one has to go for the numerical solution. Is this point clear? So even with very simple situation of one dimensional flow, if you consider the compressibility and include a real fluid, you will not be able to get the closed form of analytical solution. Okay, you have to go for the numerical solution. When we are simplifying it for a calorically perfect gas, then only we are able to determine the value of, then only we are able to determine the closed form solution. Okay. Now this type of solution procedure is actually little bit complicated. Okay, because you have to do this trial and error and then the substitution. So one easiest approach which is mainly provided in majority of the compressible flow and gas dynamics textbooks is that they provide one property table. Okay, and depending upon the value of the Mach number, they first consider a reference state, and with reference to that all the properties are actually given, so that you can just directly refer to the table, and from table itself you can actually find out the value of all these ratios, T2 by T1, P2 by P1, rho 2 by rho 1. So every time you need not to solve these relations. However, these property tables are actually constructed by utilizing these relations only. Okay, so let me try to explain how to construct these tables and then what added benefit we get from the tables. Okay, so what we can do actually, we can consider that, say, my initial reference state is nothing but a sonic state. Okay, so I can consider that my m1 is always, say for a reference state, m1 is equal to 1, and any parameter corresponding to this reference state is something which I am actually denoting with quantity star. Say temperature corresponding to this I am calling as T star, pressure I am calling as P star, and uh, density I am calling as, say, rho star, stagnation temperature T naught star, and stagnation pressure P naught star. And say, so this is what I have done. I have considered nothing but my reference state, and given state corresponding to which I want to obtain the value of properties, say that state is having Mach number nothing but any Mach number m. Is this point clear? Now please don't confuse these star quantities with the starred quantities whatever we have discussed earlier. So when we discussed the earlier starred quantities, we said that if our flow situation is other than sonic condition, then we were either deaccelerating or accelerating the flow adiabatically to reach the sonic condition. Then we were able to define over there the values, quantities as star quantities. However, here our situation is not adiabatic. So it means these star quantities are nothing have to do with the starred quantities whatever we have discussed earlier. So these starred quantities are over here nothing but designating the reference state which is corresponding to Mach number equal to 1. Is this point clear? So these star are not related to the starred parameters which we have discussed earlier. Now what I will do, my relation of P2 by P1, can you tell me? 1 plus m1 square, m2 square. Okay, so now if I do apply this formulation over here, so corresponding to, say, Mach number m, my pressure is P. So I will get P by, and corresponding to, and say my initial condition is nothing but reference state. With reference to this I am calculating the quantity. So my initial condition will be P1 by equal to 1 plus gamma by 2, because Mach number is 1, divided by okay. Then similarly I can write T2 by T1, the corresponding form in terms of T by T star as, what is the value of T2 by T1? What is the value? Can you tell me? So 1 plus gamma by 2, m1 square will cancel out, 1 plus m square, okay, this whole square of this, m1 by m2 was there, so that will become simply m square. Okay, similarly I can write down rho by Is it having some square or something, or no? Okay, so this is my rho by rho star. Okay, so this is this. Similarly, I can write down nothing but stagnation quantities. So I can write T naught by T naught star. Okay, so T naught by T naught star will become 1 plus gamma minus 1 by 2, 1 plus gamma minus 1 by 2 m square divided by 1 plus gamma minus 1 by 2. This can be further algebraically simplified. Okay, times m square okay. Similarly, I can write P naught by P naught star. P naught by P naught star will become 1 plus power gamma by, okay, then next 1 plus gamma by 2 okay. So now if you see, we have got the simple relations, and for every relation our actually reference condition is 1. Okay, that my sonic condition, and for the given value of Mach number I can calculate the ratio of all other quantities. Okay, so it means that using these relations I can construct a table where my first column can be m, next column can be p by, next can be okay. So these are nothing but identical to that of our, like say, property tables. In case of air property tables, if we consider it as an ideal gas, we refer some value of temperature, and corresponding to that we calculate the value of say U, Cp, Cv, enthalpy. Okay, likewise in case of steam table, if you have say for saturated quantities some temperature or pressure is known, you can calculate all other values. So likewise these type of tables are provided in majority of the compressible flow books, and these tables are particularly for 1D flow with heat transfer. It can be heat addition or it can be, because these relations are applicable only for 1D flow with heat addition. Okay, and now what you can do, you can just substitute the value of Mach number over here. If you just put the value of Mach number, corresponding to that Mach number you will get the ratio of all other quantities. So you need not to every time solve all the complicated relations. You have to just, depending upon the Mach number, you can simply calculate it. Okay, and these are applicable for any Mach number because reference state is actually fixed. Okay, so let me once again differentiate. It is interesting to note that if I have say some channel situation, okay, in this channel say my Mach number over here is say any quantity, say Mach number of 5. Here say my Mach number m2 is nothing but Mach number of say 3. Any Mach number random I have taken. Okay, so what will happen? If I have to calculate the value of pressure, temperature and stagnation pressure, stagnation temperature, density at this point, I can simply call that I will refer to this table corresponding to 0.5 and from there I will get the value of P by P star, T by T star. So if this is my M1, I can call this as P1 by P star, T1 by T star. Star state is same. So if I refer to this point, now I am referring to M2 tending to 3. Okay, so corresponding to this, whatever value I will get, that will be P2 by. So starred quantity will be nothing but a fixed reference state. Okay, so as starred quantity is a fixed reference state, then you can directly calculate the values, and star will get cancelled, and this by these ratios you can calculate the properties. Is this point clear? Now let me little bit more elaborate so that it should not create any confusion. What I am meaning by P1 by P star is that if I am starting from Mach number equal to 5, okay, I have added the heat. Here I have added, say, heat. So say in previous case I have added Q1 amount of heat. Okay, so here I am adding heat, but this heat I am keeping on adding till my Mach number is becoming equal to 1. Is this point clear? So corresponding to that, say my heat addition is Q1 star. So then if my output quantities over here are becoming P star, T star, then these relations, because my final Mach number has become 1, as my final Mach number has become 1, that's why whatever values I will be having, these I can designate with starred quantities, and if I apply the relations of heat transfer, I will get nothing but this is P1 by P star, P2 by P star. Now if I take the another situation, in place of quantity 1, I have taken the Mach number which was at outlet state. So at outlet Mach number was 3, and then I have added some Q2 star amount of heat such that my final condition becomes, so this will be now acting as M1, or say I can say M2 dash, okay, and M2 double dash will become 1. So now finally once again my properties will be P star, T star and P naught star. So it means in first case also we have added the amount of heat which is required to make the sonic condition at the outlet, sonic condition, and reach to the starred quantities. In the second case also what we are doing, we are adding the heat so that my final situation is nothing but once again the sonic condition. So as in first case and second case both my final condition is same, so these two set of quantities will nothing but be the same. Is this point clear? So that is the whole basis of defining these tables, because if you have to define some tables, then reference state has to be fixed. So it means because these tables are nothing but based on the relations of addition of amount of heat transfer, and as we are adding the heat, it is ultimately decreasing the Mach number. Okay, so finally if I reach to a sonic condition, then all my properties will be the same. Is this point clear? That is why what I am saying is that if I have to apply this table for this type of situation where say my one Mach number is given 5, another is given 3, first I will be referring for Mach number of 5 and calculate the quantities P1 by P star, T1 by T star from my table, and when I am referring to the same table for M2, then also I will be getting over here in denominator the starred quantities, and both these starred quantities will be the same. Is this point clear? Okay, so let me stop at this point, then further we will discuss in the next lecture. Okay.